equivariant cohomology of Nakajima quiver varieties via BPS Lie algebras. But in writing the talk, I realized I'm not actually going to say anything about these. I'll just focus on the conjecture and statement of theorem. That will be more than enough for an hour. Okay, so these, yes, like I say, this conjecture, it concerns certain quantum groups built out of the cohomology of Nakajima quiver varieties. And these quantum groups, they're sort of new. The definition is kind of useful for someone who is repelled by it's a much more conceptually satisfactory way to find things about. Until very recently, we had no idea what the benefits were, what the benefits of these algebras were. And Okounkhov's conjecture is about those dimensions, precisely that those dimensions very down. Again, part one is mostly combinatorics. So in particular, the ground field here will most often be a finite. Of finite sets and paramorphism between them. The set is the arrows in the set of vertices. That's the target. Arrow to its source and its target. Yeah, it's a very type thing, and of course you can draw them on the board, and then sometimes do some combinatorics. A field. Now I'm very agnostic about what that field is. It's Q to be the free path algebra, or just the path algebra. It has as a basis over K, and the paths in Q, including the so-called lazy paths. So EI is a path of length 0. And I have one of these for all vertices. So for every vertex, there's a path which begins and ends at that vertex and doesn't go anywhere. It has length 0. If rho is a finite dimensional K Q module, one defines its dimension vector. This is the tuple given by the K dimensions of the sub-vector spaces of rho one gets by multiplying on the left by the lazy path. So this sits inside N Q0 as one of these for each vertex. So an alternative way to think of a module over this algebra is it's a choice of a vector space for every vertex and a linear map for every arrow, which tells you how the element in this free path algebra associated to that arrow, to that one length 1 path, acts on my vector spaces. And if I just remember the dimensions of those vector spaces, I get this dimension vector. Dimension vector. And then one considers the following set d-dimensional, absolutely, so I'll come back to this, indecomposable modules over the free path algebra, where the ground field here is the unique field of order Q And for this to exist, I need for Q to be a prime power. So I count d-dimensional, absolutely indecomposable modules over this algebra. I only count them up to equivalence given by isomorphisms. So I count isomorphism classes. And this is obviously a function of Q. Absolutely indecomposable means that the module remains indecomposable after tensing with the algebraic closure of my ground field. Okay, and this, as I say, it's a function of Q. So a priori, it only makes sense if I plug into it a prime power, but it's one of the sort of foundational theorems in the subject is the theorem of Katz, Victor Katz, saying that in fact, this function is given by a polynomial with integer coefficients. So I can evaluate it at any Q. So this is from 83. And then I don't remember the year I don't remember how many years we had to wait for the following, at least 20, no, more like 25. It's a theorem of Hausel, Letelier, Rodriguez, Villegas, that in fact, this polynomial has positive coefficients. Okay, so it's kind of interesting situation where we have a fairly elementary combinatorial problem. It's really, it's a way of packaging together lots of different combinatorics problems in linear algebras, basic linear algebra. One gets this deep theorem and then this deep theorem that these functions of the cardinality of the field are given by polynomials, but with integer coefficients. And so it's natural to wonder what are the meanings of these coefficients? Do they also have some kind of combinatorial meaning or something to do with algebra or something to do with anything at all? And the first theorem, which gives one hope in this direction, it's a theorem also due to Tomasz Hausel, proving a conjecture also due to Victor Katz, which states the following, that if I just look at the constant coefficient, i.e. I evaluate my polynomial at 0, this is the dimension of a certain graded piece of a certain graded Lie algebra. So this is the Katz-Moody Lie algebra associated to the underlying graph. Or Q, and it's Z, it's the Q0 graded. So I can look at its dth piece. So D here is, just to remind you, a dimension vector. And he proved this. So at least some of the coefficients of these polynomials certainly do have a deep meaning in terms of some other branch of mathematics. And let me maybe just make the remark that if Q is ADE, meaning that the underlying graph of Q is an ADE Dynkin diagram, then firstly, this Katz-Moody Lie algebra is just the usual simple Lie algebra defined with respect to that Dynkin diagram. And furthermore, there's a theorem of Gabriel which says that only under these circumstances are there a finite number of indecomposable modules over the path algebra, and the number of d-dimensional indecomposable, or equivalently absolutely indecomposable KQ modules up to ISO. This is equal to the dimension of this graded piece this Lie algebra. So here, there's no dependence at all on the field. So this is another way of saying that under these circumstances, A, Q, D, Q is constant. It's constant. And so everything is bound up in knowing what this constant term is. Okay, so at this point, you might be wondering, well, maybe we've inadvertently got to the end of the story quite early in the talk. Maybe there aren't any higher coefficients. There's nothing more to say. Let me just do a quick example, which should dispel that suspicion. So let Q be what's often called the Jordan quiver, for reasons that will become apparent in a few minutes. So Q is a quiver with one vertex and one loop. Okay, so the K, Q, if I call my loop X, this is just the polynomial algebra in one variable, and K, Q modules, so let's say D dimensional, KQ modules up to isomorphism are in bijection with elements of the set of D by D matrices with entries in K, but up to conjugation. And what this assignment does, is send a module rho to whatever the action of X is on the underlying vector space of rho. Okay, so expanding this slightly, absolutely indecomposable. FQ modules up to iso are in bijection with matrices of the following form. So you know that at least after passing to the algebraic closure of my field, I can get every matrix into what's called Jordan normal form. And my module is going to be indecomposable if and only if it only has one Jordan block, where this lambda could be an element of my ground field. Absolutely indecomposable. Okay, so this tells us the following, that the Katz polynomials for this quiver, for the Jordan quiver, are actually independent of D. They are equal to Q always, and in particular, you can have non-zero higher coefficients. So it's the old question, Katz question, what is the meaning? What is the meaning of these higher coefficients? Right, so that's the combinatorics, and in particular, a lightning introduction to Katz polynomials. Part two is more suited to the program we're at. So moduli spaces plus geometric representation theory plus rep theory. And this part of the talk, and in fact, the whole of the rest of the talk, will now be over a very particular ground field, that is the complex numbers. Okay, so the basic idea is going to be to start off answering Katz's question by sort of revisiting the answer we already know very well, i.e. the answer to the question, how to think about the constant coefficients. And we're going to think of them in terms of geometric representation theory. Let's go higher. No. So for that, I'm going to have to define for you Nakajima quiver varieties. Apologies to those of you who've obviously met them before, but I'll be quick. So Q is, again, a quiver. I denote by Q bar the double quiver. So recall, I have to give you a bunch of vertices and arrows. So let me start maybe with the vertices. The vertices of the doubled quiver, they are identified with the vertices of the original quiver. The vertices, the arrows of the doubled quiver, these are the arrows of the original quiver union a second copy of the arrows of the original quiver, but with all of the orientations of my arrows reversed. So in here, I have a bunch of arrows A, and I denote by A star the reversed arrow. Yep. And the pre-projective algebra, So one can, in principle, define this over any field, but I'm just going to stick to the complex numbers from now on. So this is given by the free path algebra of the doubled quiver over the complex numbers, modulo the two-sided ideal generated by a single element. So I take the sum over all of the arrows of the original quiver, commutator A star. And I take the two-sided ideal generated by that and quotient out by it. So if Q is my Jordan quiver again, then Q bar is now got two loops, drawn a little bit too small, and the free path algebra of the doubled quiver is the polynomial algebra in two non-commuting variables. And then if I pass instead to the quotient given by the free projective algebra, I impose the relation that those two variables commute. And so this is isomorphic to the usual polynomial algebra in two commuting variables. Which is a nice enough example, but actually highly atypical, because these algebras are almost always non-commutative. Am I missing something here? Is there a razor anyway? Okay. Maybe I should have used the other one. What will happen if I just press on nothing good, right? It's not so bad. Yeah, I'm going to do that. Okay. Okay, so let D be a dimension vector. Then I consider M D pi Q. This is the stack of D dimensional pi Q modules. So this is some stack whose points correspond, whose isomorphism classes of points are in bijection with d-dimensional pi-q modules, and where, because it's a stack, those points come with automorphism groups, and those automorphism groups precisely give the automorphisms of the corresponding module. So what can I say about this? It's singular in general and a stack. And, depending on, both of those things might be off-putting. So in the kind of running example, Q is the Jordan quiver. This is what's called the commuting stack. C, D equals pairs of matrices, X star, and such that these matrices commute, and I quotient the whole thing by GLD. So you see, in particular, I could pick X and X star to be the zero matrix, in which case the simultaneous conjugation action of GLD leaves them invariant, i.e. that point has automorphism group given by GLD. So this thing is very stacky. And also at that point, it's very singular. So one could motivate Nakajima quiver varieties by the desire to get rid of these two words and replace them with kinder words. So how do we do that? Okay. So let zeta be, and I'm not expecting these words to mean anything to everyone, but in the end, I'll give you a precise example. Condition on IQ modules. So this will be some stability condition, and this will pick out an open substack of this stack. And I consider M zeta semi-stable, d-dimensional representations. So what this means precisely, the genericness, means that if D is indivisible, then zeta stable is equivalent to zeta semi-stable. Okay, so now I can consider this guy. This will now be a smooth stack. There will still be a stack because the points, their automorphism groups, record the automorphism group of the underlying module. Because everything is semi-stable and thus stable, those automorphism groups will all be the same. They'll all be C star. There's a way of rigidifying this, essentially getting rid of all of those C star automorphism groups to get now a scheme, and this will be a smooth scheme. Okay, so that's a general recipe for replacing these two words with these two words. And let me make this a little bit more concrete. And along the way, define Nakajima quiver varieties. So, right, given F, a dimension vector, F stands for framing. Then we define a new quiver, QF, as follows. Vertices are the vertices of my original quiver, plus one new vertex, which we just label with infinity. And the arrows, probably not giving myself enough room, are the arrows of the original quiver, union a bunch of new arrows coming in from the framing vertex, coming in from infinity. So these vertices I call R, I, N. So here I, is a vertex of my quiver, and n is some number between 1 and whatever the entry of my framing vector is at that vertex. And yes, I need to tell you where all of these new arrows begin and end. And that I do as follows. So source of all of these new arrows, they're all going to begin at infinity. And the target of r I dot equals to I. So in words, I take my original quiver, I add a new vertex at infinity, and then for each of my original vertices, I add a number of arrows going in from infinity to that vertex, where that number is given by the entry of f. Yeah. Okay. Yeah. Oh, so for this one, it's very hard to come up with a generic stability condition because for generics, the only thing I've told you about generic stability condition is if I manage to come up with one, it forces the condition that stability and semi-stability are the same. Representations of the pre-projective algebra for the Jordan quiver, those are modules over polynomial algebra in 2 variables. All of those have composition series given by length 1 modules. That is basically the only way to get a generic stability condition for some d is if d is equal to 1. And if d is equal to 1, then commutativity of my 2 matrices is an empty condition. And so I end up with A2. So it's not empty. And for d greater than 1, I can't come up with a generic stability condition. Yeah. Yeah. So for d greater than 1, the problem is that dimension vector is divisible. It's not indivisible. And part of the idea behind introducing this framing vertex is that once we've introduced it, we can extend a given dimension vector d by putting 1 at infinity. And now this is always indivisible because I can't divide 1 by anything. That Q FD, this is going to be the rigidified version of zeta semi-stable. I've not given you zeta yet, but I will. Representations of the pre-projective algebra for the framed quiver. So I'm just going to give you the stability condition in words. Stability equals that my module rho is generated by the one-dimensional vector space that rho assigns to the framing vertex. That's not quite Nakajima's original stability condition, but it gives the same maths. Okay, and this is a smooth scheme. It's a special case of this observation here. Right. It's good to have an example around this point, and that will appear in the second of the next 2 theorems. So for notation QFD, this is the singular cohomology of this Nakajima quiver variety, but I'm going to shift everything down by whatever the dimension of the space is. So in fancy terms, instead of taking the derived global sections of the constant sheaf, I take derived global sections of the constant perverse sheaf on this thing. But all that means is I shift my cohomological grading by the dimension of this guy. And QF, this is the direct sum over all dimension vectors of these things. So these things, they carry a really big grading. They carry a grading by dimension vectors, but they also carry a cohomological grading. And part of the reason for this careful shifting business is to make sure that that cohomological grading is expected by the follows. Okay, so here comes the geometric representation theory. Theorem of Nakajima, that if Q has no loops, Q has no loops. But it's not equivalent, this doesn't have loops. Then MQF carries an integrable representation, a special representation of this Kac-Moody-Lie algebra associated to the underlying graph here. And what's more, if I look at the zeroth cohomologically graded piece, this is an irreducible lowest weight rep, where the lowest weight is determined in a simple enough way by what F is. So that's the first theorem that really connects together the geometric representation theory of these Nakajima quiver varieties with the kind of thing we're meant to be studying. Recall that the dimensions of these, the graded pieces of this Lie algebra, recover at least the constant terms of the Katz polynomials. A similar looking, but quite hard to connect with this one theorem is given by work of Grojnowski and Nakajima. Now we go to kind of the opposite extreme. So here I insisted that Q have no loops. Here I'm going to say that Q is just the Jordan quiver. So somehow the worst quiver for this theorem. And I fix F equals 1. Then just tracking through the definitions, this framed quiver looks like this. And Q F bar is what's called the ADE Dynkin quiver. And it's, yeah, lots of you will already know that, in fact, this Nakajima quiver variety, QFD, is isomorphic to something a bit more readily met. The Hilbert scheme of D points in A2. And finally, right, the sort of deep result is that MQF with F equals 1. So this is the direct sum of MQFD over all D. That is, it's the direct sum of the cohomologies of all of the Hilbert schemes of A2 for all values of D. This is a irreducible lowest weight times infinity representation. And let me continue on the next thing and not make terrible mess this time. That's why I hide it. Right, so what is this algebra Highs infinity? Well, let me just tell you how big it is. It comes with a cohomological grading, because I've been careful to make sure everything comes with a cohomological grading. And in particular, I can take the characteristic function of the dth graded piece, where D is this D. So this, by definition, this is the sum over all integers of the dimension of the ith cohomologically graded piece of whatever this thing is, Q to the I over 2. So this is just the definition. And the sort of content is that this is Q inverse. That is, if I take this graded piece of this Lie algebra, it's just given by a single copy of Q sitting in cohomological degree -2. Okay, so this is sort of familiar. This is up to the change of variables, Q goes to Q inverse. This is A, Q, B, Q. This is the Katz polynomial for the same quiver, for the same dimension vector. So yeah, that's a fairly strong hint that there's a Lie theoretic answer to Katz's original question. So maybe let me refine Katz's question. And this is in fact still due to Katz. Is there some bigger generalized Katz-Moody Lie algebra? So this will be a cohomologically graded one might like to say Katz-Moody Lie algebra here, but this isn't a Katz-Moody Lie algebra, so that's going to be the wrong move. But this is a generalized Katz-Moody Lie algebra, whatever that means. So a special type of graded Lie algebra, homologically graded plus Z U0 graded. This Lie algebra such that if I take the characteristic function of the dth graded piece, I get the same relation. A, Q, D, Q inverse. Okay, so we've seen that the answer to this is definitely yes in the case of the Jordan quiver. We've seen that there's some indication that the answer might be yes for all quivers. That is, there is some Katz-Moody Lie algebra which is a great candidate to be the 0th cohomologically graded piece of this mysterious bigger Lie algebra. But there's still I've told you nothing about the higher coefficients aside from the Jordan quiver case. And that's what the rest of the talk is going to be about. And since I'm not going to be able to say anything about BPS Lie algebras at the end, let me just say a sort of historical note, is that it's been known that the answer to this is basically yes for a number of years, and that the required cohomologically graded Katz-Moody Lie algebra is what's called a BPS Lie algebra, defined using work of Concevius Soberman and then some work I did with Sven Meinhardt. There's a way of at least producing something which is the positive half of whatever this thing is. And as a kind of under the hood explanation of what's going on later, the way we prove our main theorem is by showing that the Lie algebra I'm about to present is a kind of doubling of that BPS Lie algebra. But that's the last I will say about that. So now for the rest of the talk, I'm going to be talking about work of Maulik and Okounkov, starting with stable envelopes. But maybe I feel like I've not really taken pause for breath the last 40 minutes, so if there are any questions, I'd happily take them now. If not, I'll press on. Yeah, it's an infinite dimensional Heisenberg algebra. Yeah, I mean, because I'm only really considering D positive, I only really need to define for you at the moment what the sort of positively graded half of it is. And the positively graded half of it is really easy to describe. It's this Lie algebra which has these infinitely many graded pieces given by these cohomologically graded things with the Lie bracket equal to 0. So it's sort of boring, but then when you double it, it becomes interesting. And it's a very degenerate example of a generalized Katz-Moody Lie algebra. No problem. Okay, so this is all a after Maulik and Okounkov. So now, okay, this is gonna be a lot more setup. So let F be my framing dimension vector as before, and let me decompose it into two smaller pieces. So F prime, F double prime, these will be smaller framing dimension vectors, but I'm going to need them to be non-zero. Then I let C star act on, so I fix a quiver, I fix a framing dimension vector, I fix a D, and I get my Nakajima quiver variety. I let C star act on it by scaling these arrows coming in from the framing vertex, RI1 up to RI F prime I with weight plus or minus 1, you get the choice. The arrows going the other way, i.e. the doubles of these arrows, I F prime I star. I want, in order for this to actually act on this thing, it's got to preserve the one relation that goes into the pre-projective algebra. And that relation pairs these RIs and these RI stars. So in order to achieve that, I let my C star scale the arrows going the other way with the opposite weight, and leaving all other arrows invariant. All other arrows invariant. Okay, then this gives me a nice action of this one-dimensional torus on my Nakajima quiver variety. And the natural thing to wonder is, what's the fixed point locus? And this turns out to be described in terms of decompositions of D into smaller dimension vectors of Nak Q F prime D prime times Nak Q F double prime D double prime. Okay, so the key thing is that F prime and F double prime add up to F, and D prime and D double prime add up to D. And if I have something in here and I have something in here, I can essentially take the direct sum and get something in here, where there are sort of no arrows going across my two summands. And so there's nothing being acted on with non-zero weight. That's a fuzzy proof of why this thing is true. And if you've not met it before or not had much to do with it before, the subject of geometric representation theory, crudely put, is, at least in cohomology, is the study of correspondences. So using correspondences in the Cartesian products of varieties to get morphisms between the cohomology of one and the cohomology of the other. So I'd like to use the C star action to get a correspondence between these two things. I'd like to, between the fixed point locus and the full locus. So the naive way to do that is consider the attracting set, which will depend on that same sign that appears near the top right-hand corner of that board. This is a subset of Nak Q F D, and it's the row inside here such that the limit as Z goes to 0 of Z row, it's nice to be able to say Z again, exists. Okay, so this variety, as we've seen in the case of the Hilbert scheme of points, it's not projective. So this is a non-trivial thing to ask. If I let a torus act on a particular point, it could just zip off to infinity and have no limit point. This is a non-trivial condition, and what's more, it depends on which sign I picked. Okay, so a naive but natural thing to do is to try to build a correspondence out of this guy, Nak Q F D C star times nat Q F D. And what I'm going to do is take rho to the limit as z goes to 0 of z acting on rho, and then rho. That seems, at first blush, that actually looks legit, but it's a bad thing to do. It's no good. So a basic example is if I let Q be the quiver with one vertex and nothing else, and let D equal 1, and F be the smallest thing it can possibly be in order to decompose it into non-zero things, then nat Q F D, one can show, is the cotangent bundle to P1. And let me draw that like so. So here's my copy of P1. Here's the fiber at infinity. Here's the fiber at 0. And depending on which sign I picked, my flow lines look like this. If I pick the other sign, then I reverse the direction of the arrows. And just looking at this picture, you can see what goes wrong. As I go down this flow line, the limit point is infinity, 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 infinity. When I get to infinity, it's still infinity. But then if I budge off infinity by just epsilon, all of a sudden I fall all the way down to 0 once I take the limit. So the nasty thing about this morphism is it's not continuous. Okay, which is meant to be discouraging, but not the end of the story. Here's how we come up with a sort of more intelligent cycle. So let lambda be a tuple of complex numbers. Then one defines what's called the deformed pre-projective algebra. I think that's what this is called. This is the free path algebra of the doubled quiver modulo 1 relation as before. Okay, so it's the same as before. It's the pre-projective algebra for the framed quiver, but I subtract off the sum I and Q0 lambda E I. Recall these were these lazy paths. And this is this is what's called the deformed pre-projective algebra. Okay, so I can do the same as before. I can consider these moduli spaces, FD, but for this deformation. So I have a story over the origin, which is just the story I've already told you, but I can deform it out with deformation parameters chosen from this, from this space of parameters, and just define like Q tilde be the same moduli space, but now for these deformations. And the thing is that if I pick a generic deformation parameter here, then the fiber over lambda, which this way, is affine. Okay, so that's all I'm going to tell you about those deformed fibers, because that's all you need to know in order to know that this kind of mess doesn't happen. The reason something went wrong here was that there was an embedded P1. There was a whole flow line going down to the origin, but it also had a limit point at infinity. And at that point at infinity, there was always going to be a discontinuity. And this kind of thing will always happen if you find inside your variety copies of P1. But you're not going to find a copy of P1 inside here if it's affine. So that's why that's all I'm telling you about. Right. So now we define L plus or minus to be the limit of the attracting locus, but the so this is t goes to 0, t lambda. So I don't take the attracting locus over the 0 fiber, but over t lambda, where lambda is generic. And now this does make sense as a cycle inside the sort of analog of the fixed point locus and the full locus, but now for the fiber over lambda. But then when I pass to the limit as t goes to 0, this now lives in the place it's meant to live. So this lives in the cohomology of this thing, which by Kunith, I can rewrite as the and there's an extra parameter u. This is coming from the fact that I have a C star acting. So this is comes from our C star action that I introduced all the way up there. And writing the cohomology of point mod C star u equals q u. And this is this u. Okay, so the basic move in the game at this point is you get an operation that goes from here to here. And the operation is I take something in here, I pull it back to the Cartesian product, I cup it with whatever this magic cycle is, and then I put it forward to here. That's the basic rule. It's like a Fourier-Mukai transform, but in cohomology. Okay. So via correspondences, these correspondences, fine. Stab minus from the cohomology of let me do this. Cool. We denote by this the cohomology of the Nakajima quiver varieties for our fixed framing dimension vector f prime. Okay. Fine. So finally, we're almost there. The R matrix, and I'll be a bit coy about where this lives just for a moment. This is given by using one stable envelope to go in, using stab plus to go in, and then using the other stable envelope to come out. And that's the reason I'm being a bit coy. These operations are not invertible, so I can't invert them. But if I invert u, if I localize by inverting this parameter u, then I can. So where this will end up living is endomorphisms of M, Q, F, prime tensor, M, Q, F dot prime, adjoined U, but with U inverted. And this is given by stab inverse following stab plus. So it's semi-obvious. I mean, once I invert U, it becomes, let's say the cohomology, the whole is like cohomology of the fixed point. But it's obvious for it's actually based on the original boats. Maulik and Okounkov, some other transparent. Okay, so final minute, let me just state the conjecture. Just tell you it's no longer a conjecture. Okay, so R, we can expand it in U. So R is, if I expand it in U, it's given by the density plus H bar, where this is some extra equivariant parameter. It becomes necessary to pass to the T equivariant cohomology of Nakajima quiver varieties, where T is some torus scaling the symplectic form on all of my Nakajima quiver varieties with this weight. And that's all I want to say about it. Then some operator R, U inverse. This is what's called the classical R matrix plus H bar, and then higher order terms in U inverse. The Maulik-Okounkov Yangian is defined to be the subalgebra of the products algebra over all F of endomorphisms of M, Q, F, given by residues in U of all matrix coefficients of R. So if I separate off one of these factors, I can think of this operator as being a matrix of endomorphisms in the other factor. And if I look at all of the entries of all of those matrices, I get some huge subalgebra of the endomorphism algebra of each one of these, and I take the algebra generated by all of that. And it's a theorem that not as an algebra, but at least at the level of graded spaces, this is isomorphic to the symmetric algebra generated by some smaller Lie algebra called the Maulik-Okounkov Lie algebra, where this has finite dimensional NQ0 or ZQ0 graded pieces. Okay, so that's good news because the definition I've given you is somewhat terrifying. Everything in sight is infinite dimensional, sort of 3 times over. But what this is telling us is that, yes, that's true, but there is something with finite dimensional graded pieces which controls the size of this thing. And because I'm out of time, let me just give you the conjecture. The conjecture states that the characteristic functions of this Lie algebra, because it's ZQ0 graded, I can take the D graded piece where D is a dimension vector. This is equal to A Q D Q inverse. This is a conjecture due to Okounkov, and the theorem is that it's true. This is true. All Q for all D. Okay, I'm out of time. Thanks for your patience. Cheers. All crystal clear. Yeah, it's a 2-part story. So somewhere along the line, and towards the end of the talk, so I mumble this especially fast, I had to introduce an extra, so there's some extra torus T acting on all of my Nakajima quiver varieties. And in particular, it scales the symplectic form on here with weight h bar. So h bar is some character for this torus T. And this Lie algebra, it depends on this torus. It really depends on the torus. Yeah, so the first conjecture actually is a conjecture of Maulik and Okounkov, which is the conjecture that there at least exists a Lie algebra defined over the rationals, such that I get this thing by just the most naive thing possible, just by extending scalars. So that's part one of the conjecture, and then part two of the conjecture is that the graded pieces of this Lie algebra are given by Katz polynomials. Okay, so on the BPS Lie algebra side, we associated to quiver, you can triple it and give it what's called its canonical cubic potential. And for any quiver with potential, one can define this BPS Lie algebra. And what I proved with Lucien Hennequart and Sebastian Schegel-Mejia is that Lie algebra for that particular choice of quiver with potential has this strange property that if you add in extra equivariant parameters, you're essentially not really changing anything. You're just extending scalars. And then we showed that after extending scalars, it's isomorphic to the Maulik-Okounkov Lie algebra, which a priori is only defined after extending scalars. And then that gives us that this sort of mythical algebra is the BPS Lie algebra. So that's some words in the direction of an answer. Doesn't depend. Yeah. Actually, sorry, it doesn't depend. Yeah, it doesn't depend. There's not a quick way. Let's see, no. Sorry. Why the algebra you get in the end doesn't depend. No, that's not a quick way to explain that at all. There's a way of writing down precisely what happens when you cross the wall, when you, so generic here just means actually that if here's my space of parameters and 0 is in the middle, 0 is definitely bad. And then there are a bunch of hyperplanes going through 0, which are also bad. And then everything else is good. And so answering your question comes down to answering what happens if I cross just one of these walls. And yeah, there's a precise way of describing what happens, and it's written down in the enormous book by Maulik and Okounkov.